Hi everyone, today we're going to be talking about our next group of the periodic table, the noble gases. So today we're going to be learning the properties of the noble gases. We're going to be adding them to our periodic table, which means we'll be shading those in. We're going to review how to draw Lewis structures and planetary models, and we're going to review what it is that makes a chemical stable, which is one of those properties that these noble gases have. So before you get started, make sure that you have a periodic table, some colored pencils, and a note paper and pencil to take notes with. So, the noble gases is a set of 6 elements officially, and potentially a 7th. It includes helium, neon, argon, krypton, xenon, and radon. You'll notice I didn't actually color in oganesson here. That's because oganesson is a synthetic chemical. We created it in laboratories, and we haven't actually been able to gather enough of it to determine really what its properties are. So based on how many protons, neutrons, and electrons it has, it almost certainly behaves just like the rest of these noble gases, but because we don't have enough of it to really observe it properly, we can't say that for sure. So it's not officially a member of the group. So what I would like you to do now is take your colored pencil and your periodic table and go ahead and shade in those 6 elements. Make sure that you add them to your key. And these belong under the non-metals because the noble gases are non-metals. That means they don't have the metal properties, and it means that these things are going to be gases typically at room temperature. So go ahead and pause this video, hit play when you're ready to move on. Ready? All right. So to get started, let's take a moment and have you pull out your notes, and I want you to draw neon using 2 different techniques. I want you to draw neon using the Bohr-Rutherford, also known as the planetary model, and I want you to draw it using a Lewis structure. So the Lewis structure is a lot like the planetary model, except you basically only draw the element symbol and the valence electrons. Now, as you're doing this, I want you to pay attention to how many protons, neutrons, and electrons neon has, and I want you to notice how many valence electrons it has, so electrons in that outermost electron shell. So pause the video now and hit play when you're ready to continue. Ready? All right. So let's go over this. Let's talk about how you would go about drawing neon using a planetary model. So for neon, we would always start with the nucleus. So I would look at my periodic table, and this is the information from the periodic table. I can see that neon has 10 protons, because its atomic number is 10, and it has a mass of about 20.18. That's about 20. So I would start by saying, okay, we are going to have 10 protons. I know it has 10 protons because that is the same as my atomic number. So I know that I've got 10 protons, and then I would take its mass, which is about 20, and I would subtract the number of protons from that, which is 10, and that tells me that I have 10 neutrons. So I know that I'm also going to have 10 neutrons for neon. And the reason why that works is because the mass is basically coming from just the protons and the neutrons. Electrons are so tiny that their mass can basically be ignored, so you don't need to worry about that. So this section right here I'm going to put in a little box. That's going to represent my nucleus. Now the next thing I want to do is I want to think about how many electron shells this has. So I look at my periodic table, and on my periodic table I can see that neon is in row 2. So above it would be helium in row 1, and neon is in the second row on the periodic table. Since it's in the second row on the periodic table, I know that it has 2 electron shells. So 1, 2 electron shells. So the next thing for me to think about is my electrons. Now here I have a neutral neon atom. And for this neutral neon atom, that means that it has to have the same number of electrons as it has protons. So if I have 10 protons, that must mean there are also 10 electrons. So I'm going to start from the innermost shell first. That innermost shell can hold 2 electrons. I've got 10 total. So I'm going to fill it up. 1, 2. For the innermost shell, you can put them on either side or you can pair them up. I'm not as picky there. And then I've got 8 electrons for the next shell. So the next shell, I've got, remember we have 10 electrons total. I've used 2, so I have 8 left. The second shell can hold up to 8, so this is going to be very easy. I'm just going to put 8 electrons in that second shell. I am, however, a little bit picky about how you place them. When you place your electrons in the second or third shell, I always want you to start by putting 1 in each quadrant, so 1, 2, 3, 4, and then making pairs, 5, 6, 7, 8. Getting into that habit is really going to help us when we start talking about covalent bonds. So here you can see that for neon, I have 10 electrons, 10 protons, and 10 neutrons, and this is what the Bohr-Rutherford or planetary model would look like. Now, that's kind of a lot to draw, so there is another way that people will represent this exact same thing, and that is through using something called a Lewis structure. So in the Lewis structure, instead of representing the nucleus or any of the innermost rings, you just give the element symbol, so Ne for neon, and then what you do around that is you just put the valence electrons, so only the electrons in the outermost shell, and we arrange them the exact same way that we do in these quadrants and pairs. So I have 8 electrons to use, so 1, 2, 3, 4, 5, 6, 7, 8. Oops, that last one didn't show up. There we go. So there we've got 8 electrons around neon. So this is how I would do a Lewis structure of neon. Lewis structures are very useful when we start talking about covalent bonds, because paying attention to how many valence electrons we have, and in particular whether they are paired, like these ones all are, or unpaired, will make a big difference in understanding how these chemicals can react with other things. All right, so now that we've reviewed our Lewis structures and our planetary models, let's take a moment and remind ourselves what it takes to be stable. So if you want to be stable, and remember, being stable just means you're going to continue doing what you're doing, which means you're going to continue existing. If you're unstable, you're going to change, you're going to end up as something else. But if you want to be a stable chemical compound, what you need is a full outermost electron shell, and for anything in the A groups, with the exception of hydrogen or helium, which are happy with 2, that means you want 8 valence electrons. Well, look at neon. Neon has 2, 4, 6, 8 valence electrons. It also means you need the same, you need a neutral charge, which means the same number of protons as electrons. So the same number of positive charges as you have negative charges, so those charges add up to 0. So here I've got -1, -2, -3, -4, -5, -6, -7, -8, -9, -10, plus +10. And -10 plus +10 is 0. So a neutral atom is going to be meeting this second criteria, having the same sort of neutral, no charge, no need to form an ionic compound. So the thing that's important to understand about neon, and actually all of these noble gases, is that they already meet both of these criteria. So all of the noble gases are already stable. They don't need to form a chemical bond with anything. They're happy the way they are. So pretty much everything in column 8A isn't really going to react much. That's why these things are tasteless and smell and odorless, right? You can't smell them because what your nose does is it's a complicated chemical sensor. Things have to bond with chemical receptors there. And because these things don't want to bond with anything, they're not going to touch any of the receptors in your nose. Same thing with your taste buds. Your taste buds are complicated chemical receptors. Chemicals in food bond with your taste buds, and because this thing doesn't need to form bonds, it's not going to affect your taste buds at all. So these things are odorless, they're tasteless, because there's just not really any chemical reactions that they want to participate in. They already have everything they need. So the sort of key characteristic of the noble gases is their stability. They're not going to form ions, which means no ionic bonds. They don't need to share any electrons in order to get their electron shell full. They already have a full outermost electron share, so they're not going to form covalent bonds. And of course, they're not metals, so they can't do metallic bonds anyway. So these things aren't going to form bonds because they are already stable. Now, just because they're stable doesn't mean that we can't do interesting things with them. One of the most interesting ways that we use these noble gases is by making them briefly unstable. So it turns out, if you think about those electrons as being in shells, if you give them more energy, it allows them to sort of move up to a higher electron shell. Basically, the easiest place, the lowest energy place for the electrons to be is near the nucleus, until, of course, those shells get full. That's why we always fill the innermost shells first when we're drawing planetary models. But if you give it a little bit of energy, say by running an electrical current through it, you can give those electrons enough energy to jump up a shell. Now, of course, that makes them unstable, and the electrons are going to want to, fall back down into their normal shell. But as they fall back down into that normal shell, they release energy. And for the noble gases, they release that energy in the form of lights. So that's why we have these beautiful neon lights. All of these are called neon lights, even though they're made out of many different elements besides neon. So here you can see what each light's color looks like. Argon lights are actually the one that you're probably most likely to see. They've got that beautiful purple glow as opposed to the characteristic reddish orange of neon. And again, the way that works is if we go back to our electron shell model, being in close is where the electrons sort of want to be. In the same way that water sort of wants to flow downhill, that's the place with the least energy. But in the same way that I could, carry a bucket of water up a hill, I could run an electron current through some neon, and I could convince one of these electrons to jump up and hang out in this upper energy level for a bit. But then over time, it's going to fall back down to its original position. And as it does so, it's going to be releasing light, and that light is going to be shining off in different colors. And that's everything you need to know about the noble gases.